Let's kick it up a notch with the mean value theorem. Now, this is one of those things that sounds like gibberish the first time you hear it, but then once it sinks in, it turns out to be very, very useful. So, if f is continuous on the closed interval ab and differentiable on the open interval ab, then there's at least one number c in ab such that f prime at c is equal to f at b minus f at a divided by b minus a. Hopefully you're recognizing this part as a slope formula. This is y minus y over x minus x. So this is just a slope. But here's what that really means. There will be at least one number c on the open interval ab such that the slope of the tangent at c is equal to the slope of the secant line through the points a comma f at a and b comma f at b. So that's only slightly more clear. I think a picture will help us really nail it down. So we have some function, all right, but we're only interested in a certain interval from a to b. That interval is going to be defined by a secant line. And a secant line is a line that just cuts through the interior of the function. It just cuts across a function. So this is my secant line. So the mean value theorem is telling us that there will be at least one point between a and b such that the slope of the tangent line will equal the slope of the secant line. So of course what I just pulled into the picture would be the tangent line. And so let's say this turns out to be the point of tangency right here. So if I sort of trace that down, then this is the point C at which the slope of the tangent line and the slope of this secant line are the same. That's what the mean value theorem says. So one really useful way to think about this is in the context of rate of change. So the secant line is the average rate of change on the interval from a to b. The secant is the average rate of change. The slope at c is the instantaneous rate of change at that particular point. So the mean value theorem is saying that between a and b, there's at least one point where the instantaneous rate of change is equal to the average rate of change for the interval. Let's see the mean value theorem at work. Two stationary patrol cars equipped with radar are 5 miles apart. As a car passes the first patrol car, its speed is clocked at 55 miles per hour. 4 minutes later, when the car passes the second patrol car, its speed is clocked at 50 miles per hour. Prove that the car must have exceeded the speed limit of 55 miles per hour at some time during the 4 minutes. Let's draw a graph to help us visualize the situation. So imagine that the first patrol car is here at position A and the second patrol car is at position B. So we're going to put distance in miles on the y-axis. And as usual, we're going to put time on the x-axis in hours since the speed is in miles per hour. So we'll have miles and hours. So let's start our graph right as the car passes by the first patrol car. So that happens right here, okay, right at position A. So since we're starting the graph here, we can go ahead and call this 0 miles. And similarly, this will be at 0 hours. All right, we're just starting right here at the origin. Now let's talk about these miles. We know that the patrol cars are 5 miles apart. So if the first patrol car is at position 0, then the second patrol car is at 5 miles. Okay, so this would be the point where the car is passing the second patrol car. Now, what will the time be as the car passes the second patrol car? Well, we know that this happens 4 minutes later, but we want that in hours. So let's just do a little bit of unit conversion. So let's see, 4 minutes. And we know that there is 1 hour that equals 60 minutes. The minutes cancel out. So that gives you 4 over 60 hours, which reduces down to 1/15 of an hour. Okay, so that means the car passes the second patrol car at time 1/15 of an hour. Let's calculate the average rate of change over this interval. The average rate of change is simply the slope. So we're talking y minus y over x minus x. So that's going to be 5 minus 0 over 1/15 minus 0. Okay, that's a janky 0 up there that's bugging me. So of course that means it's going to be 5 over 1/15, and we multiply by the reciprocal, so that's going to be 5 times 15, which equals 75 miles per hour. Remember that the slope of this position function is the speed of the car. And this segment that we've drawn is the average speed of the car. When the car passed the first patrol car, it was going 55 miles per hour. So the slope at that point was less than this. When the car passed the second patrol car, again, the slope was less than this. It was only going 50 miles per hour. So the slope at the end of the journey is going to be less. So if we sort of connect this up, the actual position function of the car might look something more like this. You know, we don't have an equation or anything, so we don't know exactly how it goes, but this is the idea. The mean value theorem tells us that there is going to be some point on the interval where the instantaneous rate of change, the instantaneous speed, is going to equal the average speed at some point in between 0 hours and 1/15 of an hour. So in other words, somewhere along the way, maybe somewhere right in here, there's going to be a point where the car was going the average speed of 75 miles per hour. And in fact, we can see looking at this graph, there were probably 2 times. Okay, there are probably 2 points, but the mean value theorem tells us there is at least one point where the instantaneous rate of change equals the average rate of change. So even if the police officer did not actually clock you going 75 miles per hour, if they used a speed trap like this one, they could prove that you must have gone 75 miles per hour at some point between the 2 patrol cars. I wonder if they're actually using this anywhere. If anyone knows of a situation where police have given a ticket based on this type of calculation, please leave a comment. I'm really curious. So you would write up your answer something like this. Let's look at one more example. For f of x equals 5 minus 4 divided by x, find all values of c on the open interval 1 to 4, such that f prime at c is equal to f at 4 minus f at 1 divided by 4 minus 1. So again, at a glance, this might look like gibberish, but think this. When you see f prime at c, that's the instantaneous rate of change. And when you see this slope formula, you know, this is just y minus y divided by x minus x, where the x's, you know, this is like x1 and x2. Then this will be the average rate of change. The mean value theorem says there should be at least one value of c where the instantaneous rate of change will equal the average rate of change. So first, let's go ahead and calculate the average rate of change over here. We're going to need f at 4 and f at 1, so let's do that real quick first. Let's see. F at 4 will be 5 minus 4 over 4, and that's just going to be 5 minus 1, so that will equal 4. Now let's find f at 1. So that'll be 5 minus 4 over 1, which will just be 5 minus 4, which equals 1. So the average rate of change, which is just the slope, it's just y minus y divided by x minus x, the average rate of change is going to equal 4 minus 1 divided by 4 minus 1. And of course that's going to equal 3 over 3, which equals 1. So this is the average rate of change. So we need to find all values of c such that the derivative is equal to 1. So now it's time to find the derivative. So let's remember that f of x could be written this way. So f of x is equal to 5 minus 4 times x to the negative 1 power. All right, that's the same thing, right? So now if I want to find the derivative, f prime of x, well, the derivative of a constant is 0, so forget about that. The power rule, negative 1 times 4 is going to give me a positive 4, but then I have to reduce this power by 1, so that'll be to the negative 2 power. So in other words, f prime is equal to 4 over x squared. So we need to find all values of c where this derivative is equal to 1. And according to the mean value theorem, there should be at least one of these values. So we're just going to set these equal to each other and see what happens. All right, so 4 over x squared is equal to 1. We've learned a shortcut. When you have a fraction equal to a number, you can always swap these two. You can swap the denominator and the number that's by itself. If you do that right now, you're going to get, 4 over 1 is equal to x squared. So obviously that means 4 is equal to x squared. So we get x equals plus or minus 2, but only one of these is in the interval 1 to 4. So ignore the negative 2, and we can see that c is equal to positive 2. Let's take a brief look at this graphically. So the average rate of change is simply the slope from here to here. We found that the average rate of change was 1. And according to the mean value theorem, there should be at least one value on the interval between 1 and 4 where the instantaneous rate of change is equal to that same average rate of change of 1. And we came up with the value c equals 2. So that would be right here. Boom. So if we just take a look at it, let's see. I'm just going to copy this same segment. And sure enough, that is the tangent line at 2. So that means the instantaneous rate of change at 2 is equal to the average rate of change over this interval.